How's it going, everyone? That's a little better. Hope you all are doing alright today. Yes, there is class on Wednesday, but you can watch it recorded if you have to be somewhere else. Okay. Do you have any questions before we get started? $59 and $73. So you have f of x equals e to the x plus 2. And we want to sketch a graph of this. Now, the basic graph will look like this, where our anchor points at 0, 1. And it's just a increasing curve to the right, and on the left it's converging towards the horizontal asymptote. All we're doing here is taking that graph and shifting it 2 places to the left. So our graph for f of x, instead of it starting at 0, 1, we take that point and move it left 2 places here, and we draw the same curve. Domain is always all real numbers. Range goes from the horizontal asymptote to infinity, 0 to infinity in this case. We don't need to find the other things that they talked about, which is the extra y-intercepts or anything else like that. I mean, we would just plug in x equals 0 for the y-intercept, but I wouldn't worry about it. Let me do 47 before we move ahead to the other 2 problems. '47 is also a graphing problem. F of x equals 3 to the x minus 1. all this does is it takes the basic graph of 3 to the x and moves it right 1. Normally, we start at 0, 1. We shift that to the right 1 point, so we're starting at 1, 1. And then we just draw in a curve. So both of these graphs are pretty similar. Notice we're not really differentiating the shapes of these graphs, even though they have slightly different bases. Now, base E is about 2.7, base 3 a little bit higher. It's going to have a little bit different curvature, but it's so hard to tell this just in a simple sketch of a graph. So instead of worrying about showing the difference between E to the x and 3 to the x, let's just make sure we get the graph going in the right place and going in the right direction. We should be okay from there. But again, every exponential graph starts off like this. It starts off with this main point at 0, 1, or anchor point as we called it, and then we shift it accordingly to the transformations that are given in the expression. So, all right, and then 73 and 75. We have 3 to the x squared. Yeah. 3 to the x squared equals 9 to the x. Where's that cube? What is that? What's going on there? Cube. There we go. It's an exponent in an exponent. It's a little bit hard to see just randomly looking at the page. All right. So this left-hand side has base 3, so our first thought is, can we write the right-hand side as base 3? Because again, the only way we can approach these right now that we know of is to get a base, the same base on both sides. This one's already lower than 9, so we try to get this one to match this one. And it turns out that 9 is 3 squared. Now, in this case, if we have 3 squared in parentheses raised to the x power, we multiply those together, so it's 2x. And now that the bases are the same, both of them have base 3. Cross that off. And we can say x cubed is equal to 2x. Now this is a polynomial, and anytime we want to solve a polynomial, typically we get it equal to 0. There are a few cases where we don't, but usually we subtract over the 2x, and that way we have it equal to 0. Now we can factor and solve. The only time we don't get it equal to 0 is if we're using the square root property, which is a perfect square equal to a number, and we didn't have that here. So now we have a common factor of x between these two terms. So we divide out an x. X cubed divided by x leaves x squared. minus, and then 2x divided by x leaves a 2 equals 0. We can set this part equal to 0, which gives us x equals 0. And then setting this part equal to 0, x squared equals 2. And then we can take the square root of both sides now, including a plus or minus sign on the right hand side. So x is plus or minus the square root of 2, as well as 0 in this case. Okay. Yeah. Now 75, that's the other one that Joel requested. We have 8 to the negative x plus 11 equals 16 to the 2x. Now, similar to the previous problem, we want to get the same base on both sides. Now, we look at 8 and 16, and 16 is a multiple of 8, but it's not a power of 8, because you have to think about, okay, 8 raised to what number would equal 16? And there is no such number. So, there might be a fraction. Anyway, it's all right. But 8 and 16 are both powers of 2. And so that would be our better approach in this case, is to take 8 and make it a power of 2. And the same thing with 16. So 8 is 2 to the third. And 16 is 2 to the fourth power. Now, like we talked about in 673, we can, when we have something raised to a power and then raised to another power, we distribute, or multiply. We multiply these, but in this case it turns out to be distribution on the left. So that'll be negative 3x plus 33. And on the right hand side, we multiply those. 4 times 2x is 8x. So now that both sides have the same base 2, we can get rid of that. And we'll just say negative 3x plus 33 is equal to 8x. And it's just a matter of solving the equation that we get from here. Just like the last one, just take what we get and then solve it. So this one is linear, so it's actually much easier. We'll add 3x to both sides. And then we should just be able to divide and get our answer. And if we divide by 11, we get x is equal to 3. Ooh, excuse me. Any questions there? Okay, today we're going to look at section 6.4. The plan is on Wednesday we'll look at sections 5 and 6 together, and then Monday next week look at 7.1, I believe. And I think we'll be able to go ahead and review on Wednesday next week. We won't have to have a Friday review or anything like that. Oh no, that's my stats class. Anyway, yeah, we should be okay then. So we're not going to have a formal test on chapter 6, so be sure to study it a little bit more closely. But yeah, next week will be our last week before finals, I believe. We just got to get through that, and we'll be good. So. Functions, not equations. Okay. Now, logarithmic functions first of all, let's look at what a logarithm actually is. B is called the base of the logarithm, and x is referred to as the argument. I'm not sure why we called it the argument, but that's what we call it. So, that's our general form. Now, what does it actually mean when we have a logarithm? For instance, if we say log base 2 of 8, okay? This means that we want to find the number that 2 must be raised to in order to equal 8. Okay, so when we look at that, we're thinking 2 raised to what power is equal to 8? Do you remember what that value is? 3. Yeah. So 2 to the 3 is equal to 8. So log base 2 of 8 is equal to 3. It's really just a rewriting of an exponential expression when we do it look like this. And we're going to look a little bit more closely at that connection in a moment. What if we wanted log base 5 of 25? What would that equal? 2, yeah. Since 5 squared is equal to 25, it means log base 5 of 25 is equal to 2. What if we said log base 6 of 1 over 6? -1, good. Okay. Log base 2020 of the value 1. Zero. Right. Because anything to the 0 power is equal to 1. Okay. That's just our basic understanding of logarithms. Now, there are logarithms that we aren't able to calculate in our heads, but luckily we'll be able to use the calculator for that instead. But before we start looking at the calculator stuff, let's look at the what we call a conversion formula. Our conversion formula says that y equals, wow, they all hit it once today. Y equals log base b of x converts to the b to the y equals x. That's a little silly.
Damn it, I want to hit him right there.
Sorry about that. I'm trying to find my... I wonder if I could... I can't do it through the app, I don't think. I don't know if it does any good to block those people. Oh, I know what I can block keywords, though. Channel. Let me mute because I don't want to listen to myself 5 seconds ago. How do I do that? Create a dashboard. Figure it out. No, sorry. I'm oh, may have stopped going. No, it's still going. I was trying to figure out something real quick because I know it can ban certain words, and it just the post won't show up in chat. just to stop those guys from spamming. I mean, this is done by bots, and I'm sure it's a different one each time. I don't remember exactly where I changed that. So that is something I'll have to look at later, I guess. Anyway, sorry about that. What's one of the make a note to this. Could just turn off hyperlinks and that may solve it. But anyway, let's just keep going. So our conversion formula, we have y equals log base b of x equals, or converts to and from b to the y equals x. So this conversion formula can go either direction. We can convert from logarithm to exponential, or we can convert from exponential to logarithm form, whichever one is most advantageous. In fact, anytime we're solving equations, this is one of our major strategies. If it's not solvable in one form, can we convert it to the other and solve it from there? For instance, if we had 2 equals log base 7 of x, we're not able to say 7 to what power equals x. What would that be if we convert to the other form? Well, it'll be 49. What would the conversion be, first of all? Well, the conversion would be 7 to the second power equals x. Yeah. And then we can conclude x is 49. Yeah, and really what it is just a matter of matching up. Like, we know that the conversion of y equals log base b of x is b to the y equals x. So 2 is our y, and 7 is our b in this case. And then x is our x, appropriately enough. And then when we convert that to b to the y equals x, b to the y will be 7 squared equals x. Okay, what would our conversion of 5 equals log base 2 of x? You'll have it provided for you. You'll have that formula provided, so no need to worry about that. Yeah, b is referred to as the base in both the log form and the exponent form. 2 to the 5 equals x. Again, here's y, and then b, and then x. Okay, and then 2 to the 5th is 32. Now we could also say, let's try 3 equals log base b of 27. If we convert that, what would that look like? What would it be in a converted form, though? But instead of x, we actually have, so here's y, b, and then x. Yeah, so we would say 3, oh no, we wouldn't say 3. B to the 3 equals 27. Okay. And then we could just take the cube root of both sides. And the cube root of 27 turned out to be 3. So we can use this conversion tool as a way of solving these logarithmic equations where we don't know either the base or the argument. Here we didn't know the argument, here we didn't know the argument, here we didn't know the base. So if we don't know either one of those two things, then we can convert it to exponential form and solve for it. Now, if we don't know the argument, then that's pretty straightforward. We just work out whatever exponent we get as a result. And if we don't know what the base is, we actually end up with a polynomial expression that we need to solve and get our solution for there. Now, as you said, the conversion formula works both ways. So we could say b to the y equals x also converts to y equals log base b of x. So for example, if we have anything we can work now will end up being solvable by other methods, but I'll just show you an example. 2 to the x equals 10. What would that be if we convert? From exponential form to logarithmic form. We're not calculating the value of x, we're just converting it from one form to another. x equals log base 2 of 10. In this one, we don't actually know what that value is. It's somewhere between 3 and 4 because 2 to the third is 8, 2 to the fourth is 16, and 10 is between 8 and 16. And there is a way that we can know what that value is, but we'll get to it in a moment. Alright, let's do one more of those. Now that's really the only case where we have to convert. And there's actually, that's really the only case where we have to convert is if we don't know the exponent. If we didn't know what the base was, we could just, it's a polynomial we can solve, and if we didn't know what this number was, we just work out that problem there. Anyway, we'll do one more of those. Anyway, so 3 of the x is equal to 32. I'm just using this format here. We know that b to the y equals x converts to y equals log base b of x. So if we call this b, call this y, and call this x, we have b to the y equals x, fitting this formula. And now when we convert it, that's fine. We'll put our y value first, which is x. Log base b, b is 3 in this case, and x, which is 32 inside. The book uses a for base, but I like using b for base because I think it makes more sense. Let's go ahead and look at calculations of logarithms. I know that's a little bit confusing, but we think it was a placeholder, I guess. Yeah, it's confusing to say this x is y and this 32 is x. I know that doesn't make any sense, but excuse me. Now on our calculator we have two different buttons that we use for logarithms. We have the log button, which is log of base 10. And then we have the natural log button, that's the natural logarithm, which is a log of base e. Now you'll remember we talked about e last time. That's our natural exponential, so our natural logarithm is based on our natural exponential. If it says log x, then that'll be log of base 10, but that is an important point. Now, this calculator of mine it actually just has ln and log on the same button. If it says log or log 10 or log x, it means this first one. ln is always the natural logarithm. I figured that's what you said. This one has an ln and a log on the same button. So if I press it once, it brings up ln, but if I press it again, it brings up log, and it cycles between them. I'm not sure what log base is to do any base, but we'll work around that. Most calculators do have two separate buttons. You can see this one has two separate buttons for log and for natural log. What's the y for? Log y of x? Does that mean you can insert a base there? That would be cool. Anyway, depending on your calculator, you may have to, if we wanted to find, for instance, log of 13, some calculators will enter the 13 first and then press log, or other calculators will have you press log first, enter 13, and then press equals or enter whatever you have. What is the log of 13 approximately? $1.11. That's what I got. This calculator, I'll enter log first and then 13 and then equals, and it'll give me the result. Other calculators, such as the one that's on my phone, this one I'll actually enter the 13 first and then press log, and it'll give me the answer there. So it really depends on which way your calculator operates. Now, if you just have a 0 there and you press log and it gives you an error, that means you should put the number in first. Did you have a question about the calculator, Brock? Yeah, August, go back to your question. I said log 13 here like it was nothing, but log 13 is actually log base 10 of 13. So that's another thing I needed to point out, is that logarithm without a base expressed is assumed to be base 10. So log of x is equal to log base 10 of x. ln x is log base e of x. Yeah, and when there's no base written, depending on whether it's log or ln, then we know it's either a base 10 or base e, depending on which one we have. So log base 10, log base e. So that's only two bases that we can typically use our calculators to find. Anyway, what is natural log of 30, for instance? What would that be approximately? 3.4. Make sure, even if you're, whenever you're working on your homework or if you're looking at it right now, make sure you are able to use your calculator to get these results that we're getting for log 13 and natural log of 30, for instance. That's a good way to practice. Make sure you are using your calculator properly to get those results. That's a good question, August. I suspect it may be French, but I don't know. Although the man that created logarithms was actually English, John Napier. Maybe that is one is keep the L first to indicate that's a logarithm first and foremost, and then the N is kind of a modifier on that, which makes it a natural logarithm. I can't say for sure. Okay. Now, most calculators only do those two functions. Some will actually allow you to do logs of different bases, but there are times that, whatever calculator we have, we would like to evaluate logs of different bases. And so we have what's called the change of base formula. Which says that log base b of x is equal to log x over log b. So if you don't have a calculator that handles other bases, that's fine. We are able to use this formula to be able to solve any logarithm in any calculator. For instance, what would log base 3 of 10, how would we calculate that? according to our change of base formula. Normally we look at this and say, okay, 3 to what power is equal to 10? Well, it's not really a whole number in that case. So we would do log 10 divided by log 3. That's correct. So take log of the argument divided by log of the base. Now these are both log base 10, so I didn't write the base down because they're both base 10. Anytime we have base 10, we don't have to write the base. But we can do both of these in our calculator now. In fact, we could do it all in one step if we prefer. So we would do log 10 first, and then divide, and then do log 3, and then equals. It's about 2.1, depending on how far we round it. Most of the time, and I really should write 2.10, most of the time I'll just ask you to go to 2 or 3 decimal places here. I will be sure to specify how far to go in your approximations. I think it'll probably be 2 places after the decimal, just to demonstrate we know what we're talking about. Okay. So that's our change of base formula, and it does allow for a lot of flexibility for things that otherwise we wouldn't be able to calculate. Now the change of base formula, really, it's not that we're changing everything to base 10. The real change of base formula means we can change to any base that we want, but typically we would want to change it to either base 10 or base E so that we can actually use our calculator to find it. As long as we're using the same base on top and bottom, we're good. So I generally give the formula in terms of log base 10 because I think that's the easiest for everyone to understand. That's an interesting autocorrect there, Amanda. One thing you may need to do, you may need to put parentheses around it. Log 10, parentheses, divide, parentheses, log 3. That may fix the issue that you're having. Some calculators handle it naturally. Other calculators are a little bit more needy. They need the parentheses there. And let me know if that works. Okay, good. So for your calculator, that's how you should actually proceed. And it's important that we figure this out now, and not in the middle of a test when you're in a restricted amount of time. So yes, and we went ahead and rounded to 2.10, going to 2 decimal places, The 5 rounds a 9 up to a 10, so it's 2.10. Okay. The other topics we look at in this section are the domain of logarithm functions, as well as graphing. And again, the graphs we'll do the same way we did with the exponentials. We'll start from our anchor point and move them around accordingly, basically. Okay, so first of all, the domain of logarithms. And it turns out logarithms can only be evaluated for positive values, or of positive values. Is that the best way to say that? Logarithms can only be evaluated for positive values. Okay, so for f of x is log base 3 of x. And we look at whatever's in the argument, and we solve the argument to be greater than 0. In this case, our argument is just the variable x. So we set x greater than 0. That's our domain right there. So we can only plug in positive numbers into this particular function and have them come out to be defined in real values. So what that means really is if we try to take log of 0, or if we try to take log of a negative number, neither of those would work. And in fact, if we tried to do that in our calculator, we try to do log 0, gives us an error. And if we try to do, let me clear it first, we do log of negative 2, or any negative number for that matter, that's the error. Okay, so the value that we take the logarithm of has to be bigger than 0. And that's where we get this approach. So, if f of x happens to be log base 3 of x minus 2, then we'll take that x minus 2 and set that greater than 0. We'll solve for x, and then we'll have the domain. So what is the domain in this case? X is greater than 2. Good. One last example. Which elements of this particular function will affect the domain? It's an L for logarithm. That's correct, August. 4 minus 2x is the only part of this that affects the domain. And that, again, has to be greater than 0. according to our process here. Whatever is in the argument of the logarithm has to be greater than 0. So the base does not affect the domain, and any number being added, a vertical shift, does not affect the domain. It's not inverse, it's natural logarithm. It's the inverse of the exponential function, e to the x, but that's only one specific case. Okay. There shouldn't be an inverse function on a normal calculator. You have a reciprocal function, which is x to the minus 1. That's probably all that you have, though. Like I have an x to the minus 1 right here above my x squared button. If you do have an I and V button, it's specifically to use for inverse sine, inverse cosine, inverse tangent for trigonometry. But usually you just do second, and then it has a negative 1 exponent. Anyway, that's a trigonometry or precalc question, which normally you would take either one of those after you finish this class. For those of you that are moving forward in mathematics, some of you I know are probably this is your last class, which is fine. What is the solution here? Let's see, we subtract the 4. So negative 2x is greater than negative 4. X is greater than 2? Close. Let's wrap this up first, and I'll look at that problem. Less than. And it may just be your specific calculator. Notice in this case, because we are working with an inequality, when we divide by the negative 2, then we change the direction of the inequality. Or, if you add the 2x over, and then you say 4 is greater than 2x, and then 2 is greater than x, then you flip everything around and say x is less than 2. It sounds like you did. Well, if you divided by a positive 2, you don't have to change the sign. It's only because we divide by a negative. So if we take 4 minus 2x greater than 0 and add the 2x instead, 4 is greater than 2x, we divide by 2, so 2 is greater than x. Or if we flip everything around, x is less than 2. Yeah, we only changed the direction of the inequality on division by a negative or multiplication by a negative. Which one are you referring to, Amanda? This is just finding the domain. We'll do it on paper. And that'll be like a multiple choice question anyway on the test. So the last thing I'm going to do is graph logarithms. So if we start with y equals log base 2 of x. Now, what we actually do in this case, and it's kind of strange, but what we do is we convert it to exponential form. So we get 2 to the y equals x. We'll make a t-chart of values. And we'll pick values to plug in for y instead of x. The reason we pick values for y is x is equal to a function of y here. So we have 2 to the y, so if we know the value of y, you can plug that in and then find x based on that. It's a little bit backwards, actually. Backwards from what we're used to doing. So plug in the 2. 2 squared will be 4 for x. Y equals 1. 2 to the first will be a 2 for x. Plug in 0. 2 to the 0 is 1. Plug in negative 1. 2 to the negative 1 is 1/2. And plug in negative 2. 2 to the negative 2 is 1/4. This is actually the same coordinates that we found when we graphed the exponential function, except the x and the y columns are switched. Okay, so we have 4, 2, 4, 2, 2, 1, 1, 0, 1/2, negative 1, and 1/4, negative 2. Much like the exponential function, logarithms have an asymptote. In this case, it'll be vertical instead of horizontal. And we see that the curvature is a little bit different. We go up and over to the right rather than over and up. This is actually what we would call concave down, where the exponential is concave up, but we don't have to worry about that specifically. What is the domain of this function, just looking at it? Domain is x is greater than 0. What about the range? Good. X greater than 0 or 0 to infinity. We could do it either way with an inequality or an interval. Exactly. And the range is all real numbers. Right, 0 is not included in the domain. Now this one, we can see it goes down to negative infinity vertically. This one, as it goes over to the right, because we have an arrow here, not only does it go to the right to infinity, it also goes up to infinity. But it goes up very slowly. And it looks like it's leveling off, but it's not. It will keep growing it just takes a long time for that number to grow. And that's actually one of the reasons we use logarithmic functions, is because it's a very slow accelerating function as x grows. Yeah, we cannot take log of 0, so we don't include that in the domain. Okay. Right here, though, here's our anchor point. That's where it begins, because log base b of 1 is equal to 0 for any base b. Which, I just wrote that off screen. Sorry about that. So log base b of 1 is equal to 0 for any base b. That's why we have always have the coordinate 1, 0. So the point is, we don't always have to do this thing that I just did, where we converted it and then sketched the graph by picking points. Once we know what the basic graph looks like, we can just use our transformations and go from there. So move it left or right, up or down, and then flip it over axes, whatever we need to do. So again, 1, 0 is the anchor point for logarithms. 0, 1 was the anchor point for exponentials. They're reversed from each other. You could. It's sometimes a little more tricky than others, but yes, you can. If we have a lot of transformations happening, it does make it more difficult. Yeah, most population models include exponential functions, but if we plot their growth on a chart, because it grows so quickly, we actually use what's called the logarithmic scale, which shortens the graph by quite a bit. That's way beyond what we need to talk about in this class, but in general, yes. One thing you'll notice about logarithms, well, for this chapter, it'll just be logarithms and exponents, just the basic ones there. 2 to the x, and then log base 2 of x. One of the things about the log functions is that we usually write the vertical shift before rather than after. And the reason we put the 2 plus first here like we do is it's less confusing than if we put it after, because we don't want to mistake it for being part of the logarithm. Sometimes you'll see it written after, but not exclusively. But this is a vertical shift up to x plus 3. Which direction would that go? It'll go to the left. So again, our anchor point starts off at 0, 1. We go 2 up and 3 to the left. And that's our new location for our anchor point. Now our vertical asymptote, because there's a horizontal shift, a vertical asymptote starts off right on the y-axis, but it moves left 3 also. So our vertical asymptote goes from here, 1, 2, 3 left, and now our vertical asymptote is over here. And we just draw our logarithmic curve from that point. Okay. That's what every log curve looks like, is up and over. It's actually a rotated exponential curve, is the connection, but yeah. I mean, you could go the route of plugging in points. It's just very tedious. Yeah, and that's actually what this one will be, Brock. If we get this negative in front, that's going to take the whole thing and flip it vertically. Mm-hmm. And then right 2. So in this case, again, we move to the right 2 places. So from our anchor point of 1, 0, we go right 2. Our asymptote moves from 0 to 2. But this time, because we flipped the graph vertically, it goes down and over instead of up and over. Okay. Let's see, homework. It depends where the negative sign is. Did we flip one horizontally? No, I think we flipped one vertically in the other class also. I mean, in the last lecture also. But a horizontal shift would be inside the function. Horizontal reflection would be inside the function. Vertical reflection would be outside the function. But I'm pretty sure I've purposely skipped horizontal reflection all semester. Consistently. Yeah, so that'd be a vertical flip. Yes, generally speaking. We would flip it vertically before we did the vertical shift. So we do in a way, have to follow the order of operations when we do our transformations. Let's see, so for graphs, go ahead and look at 73. 75. 79 is good. And one with a reflection. Maybe not. Anyway. Then a couple of equations to solve. 89. 91. 95. 97. Okay. Alright, that's kind of a lot of problems, but it was a big section and it's an important section, so I hope y'all give these a chance and try some of them out. Anyway, that's all we'll look at today. So you all have a good rest of the day. We will have class on Wednesday. And again, if you are traveling or you want to sleep in an extra day, it's all good. Just watch the recording afterwards, either that day or later in the weekend or something. But make sure you watch it at least. Preferably be here for the lecture so you can ask questions, but you know, as we get closer to Thanksgiving, I know that gets a little more challenging. So, yeah, just really just 2 more sections that we need to cover, and then we'll look at the final. I'll make sure I post the final review before Thanksgiving in case anyone wants to start looking at it, but that way it'll be in files. So I think that's where it goes. Alright, so you have a good rest of the day. I'll talk to you later. Bye. I haven't done the grades yet. The grades are probably not going to happen until during Thanksgiving, unfortunately, so I apologize for that delay. Sure, August. Which ones did you have? Was there a general question or more specific one? Oh, yeah. Wait, which one today? This one? Oh, down here. Yeah, negative on the outside is always the vertical flip. And in the case of this logarithm, I have a shift to the right of 2 from its anchor point. And instead of going up and over to the right, we flip it vertically so it goes down and over to the right. Did that one make sense? Mm-hmm. Now this one, negative e to the x plus 3, it might be better it might be better if we do this in stages, like figure out what... Oh, okay, I gotcha. That's a little easier, actually. So, with x plus 3 up here, what kind of shift is that? Which direction is that shift? Left 3, good. And we know this is going to flip it vertically. Now, for exponentials, our anchor point is right here, 0, 1. We know we're going to move it left 3, which puts it here. So right now, our graph looks like this. We move it left 3 with this asymptote here. Now, when we flip it vertically, we think of it as a... we're folding it down from the top to the bottom. So when we flip this graph vertically, this point actually is, since it starts 1 above this line, when we flip it down, it's now 1 below this axis. It's like we're taking the top half of the graph and folding it down to the bottom half. Why isn't that horizontal? I'm not sure what you mean. Oh, flip. Why isn't it a horizontal flip? Horizontal flip would move it from one side to the other side. True. But the motion is vertical. Orientated up versus orientated down. When we take something from the top half and put it down in the bottom half, we call that a vertical reflection. Horizontal reflection would be from the left side to the right side. Yeah, that would be a good way of saying that, Brock. Okay. Let's let's look at it like this. Remember when we did x squared? We said f of x equals x squared. We know we had this graph, just a basic parabola. And if we had f of x equals negative x squared, that flipped it down to the bottom. So it's just the same parabola, but now going the opposite direction. Instead of up, it goes down. And that's a vertical reflection. Yeah. So if we have f of x equals 2 to the x, which looks like this, then f of x equals negative 2 to the x looks like this. Yeah, with the negative outside the function, the negative is affecting the y value, not the x value. So it's affecting the vertical location, not the horizontal location. You should have time, yeah. I don't think it'll be that much of a time crunch. Well, practice it when you work on your homework and see if you can come to any realization or understanding. Okay, that'll be good. You have anything else? Okay. Alright, well, y'all take care. And I'll talk to you next time. Bye.